Good day. Welcome to the Computer Science 144 video lectures. May I remind you of what we have discussed the previous time that we had this lecture. So then I introduced the concept of stacks. Well, actually we start something slightly before that, and we discussed that we need some new data types. So we started off by the idea that we have arrays. That's a data structure. Actually, I've made a distinction between a data structure and a data type. And then I said that arrays are these types that we can use, they're built in, but sometimes we want to have data types that's a bit more, have other kind of functionality, not just the standard one that we have in the array. And so we discussed the concept of collections. In particular, we said that there are three types that we will discuss in this course. The one would be stacks. In stacks, we follow the LIFO principle. In other words, the object that went in the last time, last in, will also go out the first time. So first out, LIFO, last in, first out. Thereafter, I've mentioned that we have queues. Queues are these data types that follow the principle of FIFO, first in, first out. And then lastly, I mentioned symbol tables. Symbol tables, the prime example here is a telephone directory, where you want to find the name of a person in a telephone directory without actually searching through the whole telephone directory, but instead finding it right away, rather fast. To implement stacks, we have used linked lists. So a linked list is a recursive data structure. It's the first time that we've encountered these recursive data structures, and they allowed us then to build data types that can grow over time. So you don't have to allocate, as in the case of an array, the amount of memory before you start using it, but you can just use them. And as time progresses, you can allocate more memory as you need things, and once you don't need anything more, you just remove them from memory. Or instead, the garbage collector would actually remove them, but you would sort of remove them from your data structure, and then the garbage collector will take care of the rest. We have also implemented stacks as arrays, and there we had used a fixed array, so we specified how many elements can go in our stack. We've come to the conclusion that that is not necessarily the best idea to do things, and therefore we've also discuss the idea of an expandable array. So in other words, the array will grow over time. You double the size each time it gets full, and I've presented the outline of a proof, how you can prove that over time, on average, the timing will be in constant time. So we use the term amortized time for this particular implementation. Now today the topic will be queues. So that is what is on the agenda for today. And with queues, you are well aware of them. We find them everywhere in life. That's one of those things that you just have to get used to. There are always a queue somewhere. The example of the queue that I want to use is if you go to the Nielsen, for example, and you go in front to a place to buy some food, then you would expect that the person in front, so the person who stand in the queues the longest time, would be the person being serviced, and then so he's the first one, he's the first out. The other alternative is to say first come, first serve, and that is indeed the way queues are being used. So this is the kind of data type that we implement. Again, this is a fundamental data type, so it's not used only in for these examples that we have there, but we will find many places in your career as a computer scientist where you would use, in fact, queues. So therefore it's important that you understand them. As is the case with stacks, we will provide more than one implementation. So we will present an API up front saying what a queue should do, and then we can have different kinds of implementations for this particular queue. So let us start then with the API of a queue, and it is there on the screen. So we have a class queue, and we have introduced in the previous lecture the concept of generics. So may I remind you then that these generics are this angle bracket notation that we use there. So in other words, we can specify the type of the queue So this item is the type parameter, and this would allow us to make queues of strings, of cars, of students, of whatever you can think of. And then we have these operations in a queue. The isEmpty operation would return true if the queue is empty. In other words, there's no element in the queue. Otherwise, it would return false. Enqueue and dequeue, they have the traditional names for queues, have always been enqueue and dequeue, and for that reason we use the same names. Enqueue, we put the item to be inserted into the queue in front of the queue, and then dequeue is we remove, now we would remove the last one. Actually, if you do enqueue, it would probably be the best to put it the last element, and then dequeue, you remove the first element. I mean, you can decide how you want to remove. You want to put it in the back and remove the front, or put it in front and remove the back. So that it will give the same result. And then lastly, length there is the length of the queues. In other words, how many elements are in a queue. So with that, we can already write a small program. And so what I have here on the screen is a little program that uses the queue interface. And so I call it queue test. And so I have a string here, a queue that is of type string. So we can insert strings into the queue, and we make a new queue. And then we use the enqueue operation to add objects to this queue. So in this case, we just add strings, but this can of course be any arbitrary object that we can add. Well, of course, it should be of the same type that we specify over here. And in this case, I've just added the top 4 songs currently in the UK on Spotify. So you should probably know all these songs. And then once I've done that, I iterate through the queue. In other words, while the queue is not empty, I just dequeue the entry at the one that I've inserted the last, been the longest in the queue, and I print it out. And so let us run this example. This is the wrong window open, so I open this one and I run it. So Java queue test, and if we look down there, so we are never getting back together was the first one being inserted, then bomb bomb, then heat wave, and then good time. And so we iterate. When we iterate through them, we get always the oldest element in the queue. So that is how we would use a queue. So now the next question is, how are we going to implement this? And so what I'm going to discuss is how to implement a queue with a linked list. I have reminded you in just a couple of minutes ago about a linked list, but you will see it now again. So let us assume that we have this queue there, as it is over there. Now, of course, we want to follow the principle that we want to insert the element that we want to insert at the end, and then we want to remove the element up in the front of the queue. And now, of course, what you could do is you could keep a single reference to the first element in the list, and then every time you want to insert an element, you just use this list traversal that we've discussed a week ago. You just go through the list element by element until you find the last element, and then you have a reference to the last element and you insert the actual element over there. However, there's a bit of a problem with this approach. If your queues are really large, it means that you have to go through all the elements in the queue to get to the last one. Remember, it's impossible, as in the case of the standard arrays, where you can immediately find the point, an item in an array, you can find it with the index operator, in other words, the square brackets. But in the queue, you have to traverse the queue. Hence, we have to do something else. And for this reason, what we do is we keep now 2 references. One reference to the first of the queue, the first element of the queue, and then one reference to the last element of the queue. Now, of course, you can say, but it makes sense why we don't add as many references as possible there as needed. But it's a situation that should be taken seriously if you keep track, add another instance variables in this case. Remember, first is an instance variable of our class to be implemented, of our queue class. In the case of stack, we just use the first reference. Now we add a second one last. And now you have to update two references in all the methods that you're implementing. So you add a lot of complexity by adding an element. But in this case, it is fully justified since we cannot really afford the time to go to the end of the list. So that's the rationale behind it. So let's look at our queue here. So we have the first element, and let's assume that the last reference is correctly initialized to point to the last element. Now when I want to enqueue an element, I make a temporary variable old fast that is just a reference, and that is then pointing to whatever last is pointing. So in this case, both of them will be pointed to best. Then I make last point to a new node. So remember, with the new I create a new piece of memory, and then I let last the item to be the element to be inserted, and I make the next field null. So now we have the situation there. First is still pointing to what we have. We have the queue here, old last referring to now the old last element, and then last referring to the new element that we want to insert in this queue. And so the next step is just to link this element with that one, and so we say old last. In other words, old last dot next is equal to the last field, and by doing that we've just enqueue an element. So let's dequeue one. So we want to remove the element up front. So what do? Well, we get the item first. In this case, the item would be just first dot item, since we're removing this one, and then we just let first point to the next element. So first equal first dot next. And remember, when we do that, then this element will not have any references to it, and hence the garbage collector will come and reclaim that memory so that your program can actually use it. So afterwards, the situation looks like that. Now we have all the things together. Remember, I have to implement enqueue and dequeue, and then length, and also there was one other thing I can't remember now. Is it empty? So let us look at the complete implementation. So we have here a class queue, and item is the type parameter. So that's the type of element that we want this queue to be of. Now we have two instance variables, first and last. Then node is our private class representing this linked data structure. Remember, in the case of a node, we use that to implement the concept of a node in our linked list. And so the constructor would just make these things null. Well, they are actually null since Java will initialize them to null. Is empty. Well, if first is null, there's no element. Now let's look at the enqueue operation. So old last is the last element. If I look back, old last is last element, and then I say last item is the item to be inserted, last next empty. Now we have to be slightly careful. If the queue is empty, then it's a special case, since in that case the first and the last element is the same thing. So we have to update first as well if the queue is empty, and hence if the queue is empty, then first is equal to last. Otherwise, we just do this procedure that I've outlined here. Old fast.next is equal to last. Let's look at the dequeue operation. While the first part is easy, we get the item from first pointer, and then we just set first equal to first.next, and that is this part. First is equal to first.next. But we have to make one other special case. If the queue happens to be empty, then in other words, then first will point to null, but then last will still point to the previous last element, and so we have to make it explicitly null. Let me just draw that quickly. So if the queue had a single element in it, let's call it 2, and this is then of course pointing to null, and then we have first. Well, this is the first node in the queue, so it will point to that one. Last will point to this one. Now if I say first is equal to first.next, then essentially what I'm doing is I say first equal to first.next, and first.next is null, so the result of this is that first is equal to null. But now be careful, last is still pointing to this 2 element, but we want to remove it, so we have to update last as well. So we say last is equal to null, and in this way last is also pointing to null. So this is the special case that we have to handle when we do the dequeue operation in this case. And this is then the implementation of a queue using a list, a linked list. So now I will just outline and briefly discuss another implementation, and that is with the use of arrays. So what we have over here is we have an array of a certain capacity. Of course, we can just use an expandable array as we've done with stacks. So in other words, we have an array that will grow over time as well. Let's assume now that the capacity is 10. So what we do is we keep 2 indices, as one being tail, the other being head, and to enqueue a thing, we add it at the at position tail. We'll probably have to increment tail thereafter, depending on how you keep track of your things. And to remove an element, we just shift head 1 element forward. But now we have to be careful, since these elements, there will be elements in the list. So let me just make an example here on the well, this is not the blackboard, but on the writing pad. So in other words, say our queue is this array. So I use numbers 41, 42, 43, 44, 45, 46. Then the tail would be well, let's just add another thing to show that it's not full. So tail is over there, and then head is sitting there. Now to remove an element, what I just do is, as I said, head is equal to head plus 1. So then head is this element. So the element will still sit there, but it's not a problem. It should not worry you, since you know that head is equal to this element. But now you can see a bit of a problem. If we continue with this approach, at some point we will get to the end, and this is not a good idea. Then we have to do something, since we don't use these elements here. So one option would be to always shift the elements back up once you remove that. So once you remove this one, you copy all the elements 1 element to the left. It's a rather stupid approach, since you do a lot of calculations to copy this. So the better approach is just to let head continue by this thing, but then this queue can wrap around. So in other words, rather than calculating the value like that, we take modulo the size of this queue, so 1, 2, 3, 4, 5, 6, 7, 8. So in other words, when we get to this point, we wrap around and we start at 0 again. So in other words, we update the head value plus 1, plus 1, plus 1. When we get to this one, we start at the beginning again and continue like that. Similarly, tail can then at some point sitting there, could be tail there, head could be there. But then we know the queue is actually this element, this element, this element, this, and then starting on this side, this one, and this one, and this we don't use at that point. So this is how you would implement it with an array. I encourage you to implement, make your own implementation of a queue using arrays, preferably even with arrays that can expand over time as well. And it is not difficult. You just have to keep track of all the pointers in the, or rather not pointers, but the indices in the array. So we have multiple queue applications available, and I list some of them there. If you use iTunes or Spotify or VLC or whatever music player you use, that would be a list. The playlist, as the name says, it's a playlist, so it's a queue. Data buffers, so for example on the iPod and all those things, you would read in the data and then it would be in a buffer before it starts playing. And the other example would be if you use, for example, the Apple TV. So remember, well, I don't know how many of you use the Apple TV. Well, in the case of the Apple TV, you can play a video on your computer, stream it over the network to the Apple TV, and then that will play that to your television set. Now there's a bit of a problem if the latency in your network is a bit high and you have to wait a long time for the data to get to the actual Apple TV. You might get a jerky movie since you have not enough data to play. So what you will have in the scenario of an Apple TV, if I can maybe draw it here, is you have the televisions that sit there. There you have the Apple TV. And then what will happen is you have your computer here. So this is my computer. I send the data over the network to this side, but rather than playing it immediately, I have here a buffer. So I put all the data at the enqueue the data, and then at some point I will realize the buffer is now big enough, filled enough, and then this TV will start playing from the very start of this thing, buffer the data on the TV. You have a smooth video here. I don't know what you watch, Desperate Housewife or Cougar Town or Dexter or whatever you watch. This will start playing on this side, and as you play, you dequeue the frames to be played to this side, and you always enqueue the data that you get from the computer on this side, and in this way you have a smooth playback. And so that's the concept of a buffer, and you use them in many places. So for example, also on a hard disk, if you copy data from the hard disk to your computer, you usually put them in a buffer before start using them, so that you have enough data to use. A queue, for example, is also a concept there that on the printers, you will have a print queue, and then you actually have seen a buffer you've implemented already that's nothing other than a queue. It would be the ring buffer that you implement for your Guitar Hero application that you have implementing or maybe still implementing for the project of this course. Traffic analysis is a similar thing, and in fact for queuing applications like in a shop and those kind of things, people might be interested on how a queue behave, and so you can also use then the concept of queues to do simulation. And in fact that's exactly what we're going to do for our example. So I'm going to discuss the concept of a queue, and then we're going to simulate how a queue in a shop or someplace work. And so what we have here is we will use the so-called MD1 queuing model. Actually you can there are more general models available. So there's the MD, and then this one can also be another number. So the M refers to the arrival rate, we have the service rate, and then we have the number of servers in the queue. So what we have is we assume we have a queue here, and customers arrive at the rate of lambda per minute. For those of you who are interested in statistics, what we actually do is we assume that the arrival rate is according to a Poisson distribution or Poisson process. In other words, there's an exponential decay of when you expect the next customer to arrive, and this lambda parameter, this parameter saying what the arrival rate is, that's actually a parameter to our Poisson process distribution that we the Poisson process equations that we have there. That's actually the parameter of that. But you don't have to go into that detail. Say you don't know how this works, then you can just think of lambda as the arrival rate of how many customers arrive per minute. And then we have a queue here, and we assume the queue to be of infinite size. In other words, it can grow until infinity. Of course we don't want that, but that can work. And then we have a single server there, and this server can serve customers with a certain rate. So that is the departure rate. So that is how fast you are serviced. And with such a queue there, we have a couple of questions that we want to answer. So that is, what's the average waiting time for a customer in such a queue? I mean, so we know how they come, we know how fast the queue can service, but how long will they have to wait in this queue? Another question that a shop or a place might be interested in is, how many customers do we have on average in this queue? And so we want to try to answer this. I can tell you, I mean, since we're not doing magic here or any game that you have to guess things, there are actually also theoretical results for this particular queuing model available. So we can solve this using mathematics. It's not that bad, but I'm not going to discuss it here. It's a bit of algebra involved and statistics. However, we're going to simulate this idea so that you get an idea of to answer these two questions. So let's look at the scenario again. So here I have the concept of a queue. What I would suggest at this point, I'm not going to go through this entirely. You can do that on your own. It's perhaps a good time to pause the video at this point and make sure you understand this. Let me just go briefly through this. So we have a customer here, customer 0. He arrives at time 0, and then he will depart at time 5. Well, 5 seconds afterwards, so the waiting time is 5 seconds. Then there's also another arrival, customer 1, and that he arrives or she arrives at time 2 after 2 seconds, and we know the departure time of this customer is at 10 seconds. So this customer will have to wait 8 seconds, and then at 5 seconds, of course, this customer will be served, so it moves to this side, and now there's only one customer in the queue, and then the client 2 arrives at this point, and so forth and so forth. So we want to implement this. So what we have here is a little program that will implement this. I think I have a slightly better version, the quality of the code. So let me just open that. It's this one I should open. So it's almost there. So I can make it slightly larger. So what we have is we read in the arrival rate as well as the service rate. Ignore the code about the histogram. You have to check it for yourself. That is just to make a histogram of the data. Standard draw things to draw the actual canvas, to draw the histogram. And so the crux of the matter is this line there. So we make a queue, and that will hold the customers. And in fact, I think I want to use this instead, since it just hides some of the unnecessary details. So what we have is we start with the next arrival. So we have next arrival, and we also have the other field that would be next service. So that's the one to be service next. And if you look here, we say that next arrival is a random number from this distribution, this exponential Poisson distribution. So let's say that next arrival is maybe 2, and then the next service is the next arrival, so the one that you've shaded, plus the departing rate, the service rate. So let's say that the next service is supposedly 3. Now we sit in this infinite loop, and we do the following. We check if the next arrival is less than the next service. So if you look at the code, next arrival, next service, so in this case 2 is less than 3, so the next arrival is less than the next service, which means that we don't service this client at this moment since we haven't serviced something. So what we do is we enqueue this arrival. So this is my queue, so I put 2 in the queue, and then I say next arrival is whatever the next arrival was plus a random time. So in other words, I add a bit more time when the next arrival comes. So let's say it's maybe 4. So the next arrival is at time 4. Then we're back in this loop. We check, is the next arrival less than the next service? So let's check. I've just removed the next arrival is this value. Well, the next arrival is 4. The next service is 3. So in other words, we can service this one. So since the next arrival 4 is not less than the next service, so we have this one. So we say the waiting time is whatever next service was, so this is when I would service the next one, minus whatever is in the queue by dequeuing it. So if you look at the code here, next service minus queue.dequeue. So the waiting time is 3 minus 2, and then we dequeue this so there's nothing in the queue and the waiting time is 1. We add this to a histogram to keep track of the waiting times for different customers, and what we do is if the queue is empty, then the next service, right, we just do it as at the beginning, we add some number to this value, to the next arrival. That would be the case of thing. Otherwise, what we do is we say the next service is equal to whatever the next service was plus 1 over mu. So we update the next service. And so we continue in this fashion. You can write it out yourself again. We simulate arrivals and services. If the arrival is not the one being serviced, so if it's smaller, so let's say this is 10 and the next arrival is 5, then we would put 5 in the queue, say the next arrival is 6, we put 6 in here, so we build the queue, and then when the next service happens, we remove the first element in the queue, and that is then the waiting time is this one minus the time that that element was already in the queue. And just to show you, we can implement this, we can do this with a theoretical way, and then we get these equations. I can run this quickly for you. So I have a simulation here, and what I have here, I already have some values, so that's the arrival rate and the service rate. And if I run this, we get then this graph of showing what the waiting times for the customers in the queue. So you will see most customers don't wait that long, and there are a couple of them that will have to wait long, but most of them are serviced fairly fast. We could make it other values. So for example, I have there 1.6.22, and in fact if the arrival rate and the service rate gets close to one another, then this length of the queue will eventually go to infinity. You can think of it, and if the arrival rate is larger than this service rate, then you can think of it that is a bit of a disaster, since it means that more people is coming into the queue than we can actually service them. I mean, you can see this kind of situation typically at some offices where you would apply for some documents that you are in need for. More and more people come, and you just sit there and there's no service rate going on, and then you have the concept that people just have to wait for forever in this queue. Well, not forever, you usually get mad and you go somewhere else. But here you see already a different kind of behavior. More people will have to wait longer. If we make the service rate and these things very close to one another, let's make them the same, then you see that we really have a bad situation. Most of the people will actually have to wait a very, very long time, and being served quite fast is not even happening. So you can definitely play around with these values. This brings me then towards the end of this lecture. I want to make a couple of conclusions. So what we've seen over the last couple of lectures are that we have sequential allocation for data structures that we use. So that would be the arrays that we've used. It supports indexing. Problem is that we have a fixed size. We have then a linked allocation that I have where the size can grow, but we have these references, these pointers that we have to take care of. Linked structures are a fundamental concept in programming and the abstraction programming. So you've seen linked list. We will introduce at some point binary trees, there are graphs, sparse matrices, and all those things. They make use of linked structures. What we've also seen in the previous lectures was stacks. Stacks are built on this LIFO principle. We also have queues that we've discussed today. The idea of queues are, of course, that they follow the FCFS, first come, first serve, or FIFO, first in, first out principle. I have implemented queues with linked list, and I've discussed the implementation with arrays. And then finally I've presented an example where we use queues, and the particular example that we have here was to simulate queues actually. So how long people will have to wait in a queue and what the average number of people in a queue is. And that's the example that I have presented. So this is the end of the lecture. In the next one I will answer some questions, do a Q&A on questions from this work I've seen that I've gathered actually from the textbook, and I will also discuss the concept of iterators. Until the next time, goodbye.